Now let's talk about water. Why is water so important to the human body? So we're going to talk about five properties of water that make it so important to us. So I'm going to write them up and then we'll go through each one. Alright, cool. So here's some properties of water and let's see what that means. This first one is high heat capacity. So here's a pot of water. Okay, and got some water in it. And I'm adding my fire below. Those are some flames. Okay, so high heat capacity. Capacity sounds a little bit like capability. So whenever we say high heat capacity, water has the capability to reduce changes in temperature. That's what high heat capacity means. Water can resist changes in temperature. So let me write that. This triangle is a delta symbol, and it's often used as change. So this is resist change in temperature. Why would that be important in our body? We know that our body is made of 80%, 60 to 80% water. So why would having a high heat capacity be important? Well, if you remember in our last lectures, we mentioned this concept about homeostasis. So we only have a certain range of window. I don't know the exact range, but we want to stay around 37 degrees Celsius or 98.6 degrees Fahrenheit. So because our body is made up of a bunch of water, even if we exercise super hard or we're outside laying in the sun all day, regardless, we have this way to stay within our homeostatic range by resisting this change in temperature. But let's say our body does get really hot and we're about to be out of homeostasis, so we need to lose some heat. Then this second part comes in, this high heat of vaporization. So let's explain this next. So this is someone's skin, and we have some droplets of water. Okay, as you start exercising, your body starts getting hot and you start to see sweat droplets form on the top of your skin. So what you're doing is you're releasing water, and vaporization is actually a change of matter from liquid to a gas. This is what vaporization is. So when we say water has a high heat of vaporization, we're looking at how much heat it takes to change water from this liquid to gas form. Since it's a high heat of vaporization, it takes a lot of heat to go from a liquid to a gas form. That's advantageous for us because it works as a great cooling mechanism. So what happens is, as we're getting hotter and hotter, we start sweating and sweating. And then we have this water, and within the water we can start filling it with some heat. So I'm just going to fill in red. So we can fill in this water with all this heat, and as it's getting heated up, it eventually gets to the point where it can turn into from liquid to a gas, and it will go into a gas and get swept away by the wind and cool us off. So that's what these two things are doing in terms of high heat capacity and high vaporization. Let's look at them one more time and see how they're different, and then how they're both advantageous for us in the body. So to review one more time, high heat capacity says that we resist changes in temperature. This is good because as we increase a bunch of heat, maybe we don't have control because it's a really, really hot day outside and we start warming up, our insides get hot because we're exercising outside. We want to stay in this homeostatic range. And water having a high heat capacity, being able to resist that temperature, is going to allow us to stay in homeostasis. Eventually, though, you're mowing a lawn for an hour or something, your muscles are working really hard, you're creating all this internal heat. You need to get rid of that heat some way to stay in homeostasis. So to do that, you release water to the skin in the form of sweat. That heat can go into this water, and then as it evaporates off, it vaporizes. Evaporization, or evaporating, is the same thing as vaporizing. So it evaporates away and the wind will come and take that heat away to cool us off. Okay. So that is high heat of vaporization. Next is universal solvent. He's made this statement before. For things to be biologically active, they have to be dissolved in solution. So for things to work, if your cells need some glucose, if your cells need glucose, then you have to dissolve that sugar in water. Luckily that your blood has a ton of water in it, so as glucose is traveling through your blood, it's in solution, so it's biologically active. If you just have table sugar on the counter, it's not going to do any chemical reactions unless you add some sort of solvent to it. So let's distinguish solute versus solvent, because that can kind of trip people up sometimes. So solute versus solvent. What is being dissolved versus what is doing the dissolving. If you can remember that water is the universal solvent, then you'll know that things get dissolved in water. So you know that the solvent is the thing that does the dissolving. Solute gets dissolved. But I have a little phrase that will help you remember it too. And let me draw a picture to help with that. So this is a bank. Okay. Inside the bank, we have a robber with his loot. So here's his loot. And the cops are coming. So here's the cops. These stories, I think, really do help you remember it, because you can use this on your test if you can't remember this little phrase of dissolving or gets dissolved. So anyways, you have a thief and he's taken his loot, but the cops are coming, so he stores it in this vent. This is a crappy vent, so instead let me put the vent up here. So he's going to put his loot in the vent. The thief puts loot into the vent. So you put your solute, you put your thing, the thing that you have, you put that, you store it into something, or you dissolve it in something, and that's the solvent. So hopefully that story helps. The thief takes his loot and he puts it in the vent because the cops are coming. So you're going to take your solute, like your glucose, and you're going to dissolve it in your solvent, like your water. Alright, hydrolysis. This is, again, we're going to start breaking down words when we can into roots to try to see what they mean. So let's say I've never seen this word before, but I know some roots. Lysis, we've heard that one before. Lysis is to break apart. Hydro means water. So what this means is to break something apart, break molecules apart using water. And these are important in catabolic reactions. So remember, catabolic are our breakdown reactions where we take something bigger and we turn it into something smaller. So let's just say I'm not going to do any specific reaction. I'm just going to draw our molecule here. This is our big molecule and we want to use water to break it down. So here's an H2O. And another way you can draw this is HOH. So what this can do is it can come here and break this bond, and instead of having this bond, you'd have something like an H here, and then you'd have another molecule with an OH there. So you're using water to break something up. Here's water, break something up, and then you just add that hydrogen right there, this proton right here, and you add this hydroxyl group on this side. So that's hydrolysis. So the opposite is condensation. These are also called dehydration synthesis reaction. So we already talked about synthesis reactions and the types of chemical reactions in the first set of videos. So a synthesis reaction is when you take A plus B and you make AB. So for dehydration synthesis, then this is a reaction where we put something together, we synthesize something by dehydrating it. D means away, it means remove, okay? And then this is hydration, so water. So we're synthesizing, we're putting something together by removing water. Let's see what that looks like. So in our last example, we had our big molecule and we broke it into two things, two separate molecules, and we had our H and OH. Now, let's take that same reaction we have a molecule that has an H, and we have this molecule that has an OH. These aren't O's, these are just some groups. We'll say they're amino acids for now, okay? So these are all amino acids. One amino acid has an H on it. This amino acid has an OH on it. These two things can leave, and we can put these two parts together. So this would form, again, our 4 amino acid protein plus a water molecule. So we're synthesizing a molecule, which is this molecule right here. We're synthesizing a molecule by removing water, by dehydrating it. You dehydrate it by removing this hydrogen and this hydroxyl group, or this OH group. And then cushion. Go ahead and punch a brick wall, and then instead this time get a water pillow and put it in front of it and punch the brick wall. You'll see that there's some cushion. Sorry, that's the first thing that came to my head. So, but in our body, we have water all over, and really this is protecting our internal organs. So you'll see fluid everywhere, but we have fluid in our joint spaces to help cushion them. We have fluid surrounding our brain, the cerebrospinal fluid, helping out with that. One thing I do want to note about this universal solvent, if you remember in chemistry class, the term like dissolves like. So water is a universal solvent for polar molecules. So if you mix oil with water, you know that when you mix it, it doesn't mix well. Like they separate, right? You can see those little circles of oil within the water. So it has to be a polar substance to be dissolved in water. All right, nice. So we went through, right now what we've done so far is we've gone through the different types of, we basically very briefly classified organic versus inorganic compounds. We talked about dissociation versus dissolving, and then we talked about the properties of water that make it important to humans. Now we'll get into pH, acids, base, and salts.